Welcome to the Omar Alayli podcast, your go to podcast for exploring the diverse fields driving space exploration and technology. I'm your host, Omar Alayli, and today I'm thrilled to have a special guest joining us, Manuel La Rosa Betancourt, the co founder and CEO of Neutron Star Systems. Neutron Star Systems is pushing the boundaries of electric propulsion with advanced superconductor technology, and I can't wait to dive into that with Manuel today. Manuel, it's a pleasure to have you here.
Thank you, Omar. Thank you for the invitation and thank you for featuring in your podcast what we're trying to achieve at Neutron Star Systems.
Perfect. So I've known you since 2022 when both our startups were based in Cologne before you moved NSS to Munich. And I have found out that at your core, you're both a material science engineer and an entrepreneur, which perfectly explains your focus on high temperature superconductors and the technologies you're developing. Could you share a bit about how your background in material science led you to focus on superconductors and ultimately space propulsion?
That was a long journey. Actually, I started this 7 years ago. As a material science, I came across different types of material technologies. So I work with ceramics, with rubbers, with metals, and alloys. I did this in several industries, in the chemical industry, material science industry, plastics, rubbers. And 2014, I became independent and I founded my own consulting company. And at that time, I had the opportunity to work with Fraunhofer Institute. I was serving as a consultant for uh, pushing and articulating strategies to commercialize low TRL technologies developed at several institutes at Fraunhofer. After that, I work on specific technologies for deposition of materials based on plasma spraying. And that led me to work with for a Munich based company called Tiva. Tiva is the largest manufacturer of high temperature superconductors, and at that time, I was given the task to search for technologies that can be enabled by the use of high temperature superconductors. I did my homework. We identify as a more promising markets for these type of technologies, the defense and the space market, also the aerospace. And on that search, I came across the Institute of Space Systems at the University of Stuttgart, and I met there the head of the chair of plasma wind tunnels and electric propulsion, Dr. Georg Hedrich, who happens to work on the development on a really interesting electric propulsion technology called applied field magnetoplasma dynamic thrusters. This technology with large heritage, global heritage in United States, Japan, Russia, China, developed since the 70s, got a stock on its research because at the time that the programs were drafted, superconductors were not commercial off-the-shelf products. So there was a limitation on continue the development of this type of technology because the maturity of an important component for this technology was not there. In 2016, high temperature superconductors were already off the shelf materials and they can be commercialized by from different companies worldwide. There were production capacities. And I made the decision of going into that and partnering with Professor Hedrich, and we just, we started seeking for European funding. And that led us to get 2 awards from the European Innovation Council, one for the use of superconductors on reentry systems, and another one for the use of superconductors on electric propulsion systems. And after that, yeah, well, I got my co-founder, Marcus, etc., and here I am. So that is, in a nutshell, how do I come to this? It was a little bit of luck, and if you ask me sincerely, I found Professor Hedrich in Google.
Oh, wow. That's really fascinating, Manuel. Before we get into the propulsion systems that you're developing, can you introduce our listeners to the concept of superconductors, especially high temperature superconductors? Most
Absolutely.
people, yeah, most people might associate superconductors with physics labs and research. So, how does this play this role in space?
Not at all. Not at all. I mean, superconductivity is a physics phenomenon that occurs when electrons can pass through a material matrix without experiencing any type of resistance. Because of that, they can carry a lot of current without generating heat, which has a tremendous impact when you have to build power dense um, applications. And that is why, for example, superconductors can be applied, and wind turbines for offshore parks can be applied in high voltage DC grids, and electrical motors, generators, magnets for MRIs and health tech. And they can do that only if they are operated at a given temperature. And you have low temperature superconductors and high temperature superconductors. What that means is that low temperature superconductors has to operate at least at a 4 Kelvin temperature, and that is almost close to the absolute zero. So it's minus 264 something degrees Celsius. High temperature superconductors, by contrary, can operate at 77 Kelvin. And that was a breakthrough and a groundbreaking discovery when it was done in 1986, because um, the cryogenic system requirements to keep the superconductors at a temperature where superconductivity takes place was not as high as you have it when you have to build something with low temperature superconductors. As a matter of fact, you have the particles accelerator at CERN. It operates with low temperature superconductors. So imagine the cost, the energy consumption of keeping cryogenic cooling system at a 4 Kelvin, which is almost the absolute zero space. So by increasing the temperature at which superconductivity can take place, um, you achieve many things. You achieve a higher degree of compactness. You achieve lower cost on making the application, and here's where the trade-off comes. Where do you use superconductors and where not? And normally you use it there where you need to generate or to create power dense applications. And the reason why I did that was because even though on the terrestrial application side, the maturity of superconductors is very high, and there are commercial applications for cables, generators, etc., the best environment to operate with superconductors is space, because you don't have to cool down there. So and that have a direct implication when you want to scale um, uh, yeah, applications, spacecraft, space stations, etc. in space. And yeah, that is
That's
that is in
that,
a nutshell superconductivity.
that's so cool. I know that superconductors have a lot of emerging applications in space, just like you said, you're hoping to achieve. Could you give us an overview of some of these space applications you're particularly excited about, and what neutron star system is actively working on this area? like for shielding, active shielding, magnets, sensors?
Okay, so electric, yeah, okay. Let us go quickly. Electric propulsion is one of them. Reentry is one of them. Cosmic radiation shielding is another one. Extremely important if you want to do a space travel, and power management and distribution, which is also extremely important when you want to build large infrastructure. Because normally, compared to conventional technology, cabling on high power structures takes at least 30% of the total weight of the spacecraft. And this can be minimized by superconductors. There are other applications um, uh, like railing or magnetic rails for launching a spacecraft from the moon, for example, where you don't have the issues of gravity. Also, you can use it for photonic sensors for quantum computers. And especially in reentry, it has two is a dual use type of application because you can use it for space reentry and cargo reentry, but you can use it also for flight control and hypersonic student of hypersonic vehicles.
Cool. So when you're talking about reentry, the magnetic emissions that comes out from the superconductors, electricity going through the magnets will push away the plasma, right? That
Yeah, I
forms
mean
during
that's
reentry.
that. Yeah, that's absolutely right. I mean, you this is something that is called magnetohydrodynamic kind of aerobraking, and it can be done because magnetic fields can interact with plasma fields and ionize plasma, and by doing so, they can push away the plasma boundary layer around the spacecraft. In other words, they can increase the distance of the plasma to the spacecraft, and by that minimize the heat fluxes
Oh,
that
yeah.
that result out of that, and that's why that have an impact on the weight of the thermal protection systems. They have an impact on the volume that you can achieve for a payload maximization. And also, it have an impact on the safety of the cargo or astronauts that are going to be brought to space because you can make it more safer. It also can create a magnetic window that allows for mitigation of communications blackout.
Okay, cool. Great. Now let's shift gears to the bread and butter of neutron star systems, electric propulsion. For the listeners who might not be familiar with the field, could you explain in simple terms what electric propulsion is and how it differs from traditional chemical propulsion systems?
Right. Chemical propulsion systems operate on the ground of burning or, yeah, converting the energy of a propellant into kinetic energy. And the process take place that they can generate at really high thrust. Um, the disadvantage of that is that in order to escape a space Earth gravity, you need a lot of propellant for every kilo of payload that you need to bring across, and that means that reduces the payload capacity of your spacecraft. That's why you have these large rockets, and then only at the top you have the payload capacity that you can bring. Um, if you move around things in space, also with chemical propulsion, you will have a similar correlation. It's something like 4 or 3 to 1. And this is something that you don't have with electric propulsion. Electric propulsion also converts the propellant, the inherent energy of a propellant that is being ionized. And then once this propellant is ionized, you can accelerate this propellant by means of electromagnetic forces or electrostatic phenomena. And the the main difference is that for that, you don't need as much propellant as you need in chemical propulsion. As a matter of fact, you need like a quarter of a kilo of propellant for a kilo of payload, and in chemical propulsion you need four to one. So the savings on propellant consumption, on efficiency, are bigger, and that makes it so attractive for example, applications like last mile delivery. So we have all these micro launchers in Europe, and integrating electric propulsion in the second or third stage will be a very interesting value proposition to increase the payload capacity that they can offer to the customers.
Oh, great. So, okay, like you just said, like we typically hear about three types of ion and plasma propulsion: the electrostatic propulsion, the electrothermal propulsion, electromagnetic propulsion. Can you
That is right.
briefly can you briefly break down these categories? And I understand that your startup focuses on electromagnetic propulsion, right?
That is correct. That is correct. So, electrothermal propulsion is an interesting type of electric propulsion because it can work without having electrodes, and that have a tremendous impact on the erosion and the lifetime. However, the specific impulses that you can achieve are relatively low, and they can get up to 1,200 seconds on a specific impulse. Hall effect thrusters or electrostatic type of propulsion, um, they can provide fairly high thrust compared to other electrothermal and electromagnetic, but the specific impulses that they can deliver are not so high. That means at the long run they cannot assure a high use or an efficient use of the propellant. And in electromagnetic propulsion, they can offer both. They can offer high thrust on the one end, but also high specific impulse. Also, the electromagnetic type of propulsions, they have a higher flexibility on the kind of use of propellant that you cannot have on Hall effect thrusters, for example. They operate at best with krypton, with xenon. However, uses of argon or other type of propellants um, does not give the thrust needed to compensate drag from the atmosphere, etc. So yeah, those are the three major differences, and the electromagnetic propulsion have the advantage that it can be easily scaled up to higher powers. Hall effect thrusters after 20 kilowatts, the scaling is complex because you have thermal issues, thermal management issues, and you have increases on complexity, weight, and complexity, weight, and efficiency. Electromagnetic thrusters, by contrary, can be upscale more efficiently.
Okay. So superconductors, I've read on your website and talking to you before, seem to play a big role in your electromagnetic propulsion system. What are the main advantages of using high temperature superconductors in your thrusters, and how does it thus improve efficiency and performance compared to traditional systems?
Right. Okay. The main advantage of superconductors is in the case of electromagnetic accelerations, you need electromagnets. And up to now, those electromagnets were built with copper coils. However, these copper coils are power hungry and very inefficient. And they are limited on the type or on the size of the magnetic field that they can generate. Superconductors or high temperature superconductors don't have that problem. You can generate large magnetic fields, and those large magnetic fields are important for extending the lifetime of the thruster, just because due to the physics of the acceleration mechanisms of the thruster, you can extend the life of the electrodes, for example. You can, for example, allow power regimes that works at high voltages and low currents, and these have a positive impact on the erosion that the electrodes can experience due to the plasma that they are expelling or exhausting through the nozzle. Also, superconductors can offer, they can scale. You can scale from thrusters of 5 kilowatts, 10 kilowatts, 50 kilowatts, 100 kilowatts. And that is something that is a really compelling proposition. Another point that you have is that these superconductor coils, they can be loaded inductively by another type of superconductor application, which is called a high temperature superconductor flux pump. That means you don't have electrical joints that uses electricity or passes electricity at 80 degrees into a superconducting coil operating at 200 or minus 250 degrees. And this is quite important because the cryogenic system requirements that you have for such system are much lower. And of course, your whole system is more efficient and more scalable.
You've been dedicated to neutron star systems full time since 2019, as I know. And in 2022, you won your first contract with the US Air Force Research Lab, if I remember correctly. But around the same time, two of your co founders stepped down, which I imagine must have been a huge challenge. How did you navigate that difficult period, and
Uh,
what kept you motivated to push through?
wow. I believe in myself. I have to say that if you truly believe on what you're doing, and if you truly believe in your capabilities, I think you are unstoppable. And I think that that's the main reason how or why I could deal with many of the challenges that we face as a company. I mean, is this normal for the startups that you have conflicts with your co-founders? That is extremely normal. And in the case of Neutron Star Systems, I mean, we have been bootstrapping since 2019. My co-founder itself, he was a young person, or is a young person, also with the wishes of having a family and etc. So after 3 years bootstrapping, it was important for him, to turn the page and look for a better perspective for his girlfriend, marrying, etc. So these kind of things happen. What I learned on this journey was that politics in startups are not good. You see, politics and startups are absolutely killing. Well, in the case of our traction in the United States, I think that yeah, I mean, for this type of technology, that in my opinion can be regarded as strategic for national security, it was a great support and a great advantage to have this contract in the United States. However, you cannot keep these things if you don't have the support of your home country, right? You see, because at the end of the day, it's a space technology and it costs a lot of money to build it, to qualify it, to test it, to demonstrate it in space. I could do this because I have a huge network of supporters and a huge network of a great team of advisors that were helping me to steer and navigate through these difficult times.
Although with this drama of 2022 that happened to you, I think in 6 months or 9 months you won an award in Europe, and which kept you started you kept going. So you did all before turning the lights off. You just
No, I mean, listen. That's it's good that you mentioned that we were close to death, or to insolvency, or to to turning off the lights several times. That one was a really tough one. But I have to say that we could get that grant because of the resilience also of my co-founder Marcus. He even though he stepped out, he committed to deliver our third proposal for the same topic at the European Innovation Council. And the third proposal went through. And with that proposal, another proposal for the European Space Agency also went through. So it was teamwork. I couldn't have done it alone. Uh,
So now, looking ahead, how do you see your technology shaping the future of satellite operations and space missions?
I mean, it's not my technology. Mm, first and foremost, is a global technology. So there are other companies pushing this technology through. And as a matter of fact, when we did our first proposal for the European Innovation Council, we did this together with a small, with a not a small, with a institute of New Zealand called Robinson Research Institute. They, even though the proposal was not accepted, they took the proposal home and they got the backup of the New Zealand government. And they got 7.5 million euros to build a thruster of the same technology. Um, so I think that AF MPDs and Supreme Technology will fly, given our current financial challenges. I do not know if we will be able to make it fly in Germany and Europe, because it's a very tough environment, and there is not really a market in Europe for this kind of technology. I think that Germany and have all of the elements. You have a team, you have a that is pushing the technology at a commercial and scientific level. You have the heritage. It has you have the network, etc. But this is a market, and competition never sleeps. So I think that AFMPD thrusters will rule the market for high power spacecraft. And it doesn't matter uh, how good and how much heritage you have on Hall effect thrusters and treated ion thrusters. At the end, the market always goes for the most competitive, affordable type of technology, and that is ours.
Do you think you can give like a hypothetical case study for electric propulsion so that people who are not very much deep into propulsion systems can visualize it in their head?
Yeah, that's the beauty. I mean, with this type of electric propulsion and given the scalability that it offers, you can do Earth observation satellites. You can do a space situational awareness satellites. You can do geocommunication satellites, secure communication satellites, space togging, space satellite servicing. Assembly and manufacturing space is an ideal use case because AFMPDs can be integrated with chemical thrusters due to their propellant flexibility. And because of that, you can have a single propellant architecture and two type of modes, really high thrust and really high specific impulse. And that gives you a degree of maneuverability that is extremely important in the current space domain, mostly because of the issues of degree. So, as a matter of fact, that is where I see one of the most sweet spots for this type of technology. And then, if you want to articulate a moon economy, then you will have to achieve certain levels of economies of scale by transporting large quantities of payload. And for this, AF are the best choice because they operate on propellants like argon, which are like 10,000 cheaper, 10,000 times cheaper than the state of the art, which is xenon. And they offer the degree of scalability that you need to move from 800 kilos up to 10,000 kilos of material. And that is a very wide spectrum of applications that you can cover with one single technology. So, with that, indirectly, you will have a high degree of modularity on your space, on your satellite bus, on the core of the architecture that you're going to use for your satellites.
Okay. Do you think that, like for smaller satellites or microsatellites, they can be utilized for even orbital change?
Well, first of all, AF and PD thrusters, they offer the highest thrust density among the other electric propulsion thrusters. There is, for example, gridded ion thrusters, but they have all the limitations in terms of a specific impulse, etc. They can be used for a wide range of orbital maneuvers, rendezvous proximity operations, docking, delta V orbit changes or corrections. Actually, I don't see limitations in that sense. I see a lot of flexibility on the operational envelope that these thrusters can do.
Is there a way to decouple the thrust output from the power requirement? Because that's the only way, from my perspective, that you can achieve higher thrust.
Decouple the trust is I don't think, for at least for this type of technology, is not possible. And the reason for that is um, um, uh, with the scaling of power, then you scale also the mass flow rates of propellant in your thruster. And with that, you increase also the kinetic energy that you can generate out of ionizing the plasma and accelerating it. So with that, you increase the thrust. If you want more thrust, then you need more power. All right. So, and that is what is called the power dilemma in space. I think that there are technologies that can offer an alternative to that, but I have fear that the technology readiness level and the maturity is still not there for for articulating a real change on the state of the art for space technologies.
Gotcha. Okay, let's shift gears a little bit here. On social media, you've been quite vocal about agency and budget cuts in the last few years in space funding, especially in Europe and Germany. What do you think needs to happen to turn the situation around? How can space industry like better position itself to get more political and financial support?
Okay, let us talk perspective. No, I think that at first we need to demystify the way we regard space technology, because let us be honest and see our be aware of our own being. We're only 50,000 people worldwide. This is a really small industry, right? And I think that one of the things that we need to change, and I discussed this with one of my advisory board members, is that we need to focus more on the customer, on getting paying customers, you see, instead of focusing on technology, building stuff that nobody wants to buy. And I think that this is one of the biggest challenges that everyone on the space sector has today. So regarding the agencies and the policy in Germany, well, what I can tell you, listen, They are leaders and politicians that understand the impact and the significance of space, and there are politicians that don't. And I think that, yeah, Germany have politicians that not really understand what is the significance of space for space economy, and especially for the future of Germany as a economic power. There is, as a matter of fact, a doctrine and a kind of like a dogma, doctrine, ideas, train of thought, that says that you cannot remain a world power if you do not become a space power, right? And people agree with that. Some people don't agree with that. German politicians, I don't think they even consider dealing with this question at this point in time. And uh,
So how can we better position ourselves as part of this industry to help politicians, help this
yeah,
ecosystem improve? Is it like, I think, are we relying too much on agencies?
no agency, but that is absolutely the problem we have at the moment. You see, because the space economy is driven by governmental funding, right? So if governmental funding is not there, then the ecosystems of the space companies that bring technologies that can potentially secure some predominance in the future will die. And this is something that you see every day. You see Rocket Factory Augsburg. They worked so hard to get the funding, and now they lose the first stage. Now they have to rebuild this new first stage, and just try to imagine how much money they will need to do so. And especially, that's not the problem. The problem is where do they get this money from, right? So this is in my opinion, the way that we can position ourselves. I think I think the majority of the space entrepreneurs that I have met, etc. I mean, everyone is doing the maximum that they can. Everyone, you see, I don't wanna be the pointing out of the boo man, but I will quote on as I will citate Christine Lagarde in a intervention at the European Parliament, where she was encouraging leaders and politicians and to speak with space entrepreneurs. You see, to talk to these innovators, to talk to people like you, like me, like Thomasine, like the guys from RFA, Elena Hubi, all of these people trying to do this stuff. They need the political support, political endorsement, and also they need visibility. And that's something that really difficult to achieve in the current space economy and ecosystem, because it is populated. You have a lot of players putting stuff. I mean, everyone is building something, but then the question is, what is significant, what is relevant, what is not so relevant? What do we need to articulate capabilities that we need in the future and that make us be in the leading side of the market in the future? And that is something that is absolutely a huge challenge for everybody. I wouldn't be able to describe in words how much I am grateful that we got the support of Toon Venture Labs Aerospace, especially from Florian Botza. Unfortunately, all these incubators in the German and French ecosystems, etc., they lack the power and the influence to really, really create a change in the market, because uh, everyone in the ecosystem has to play along, and you don't have the investors ecosystem playing along with all of these initiatives.
We haven't reached critical mass yet. So I
No,
want to, no, yeah. So just want to come back to NutriStar systems. At what technical readiness level are your electrical propulsion thrusters currently? Do you? I'm not sure if you can disclose that, but I'm just
no,
wondering.
absolutely. This is all open knowledge, public domain. The current TRL of the technology is 4. That's the prototype existing at the University of Stuttgart. And within the EIC Supreme project, we are aiming to reach TRLs 5. And actually, we have a planned CDR in November, where we're expecting to freeze the design and then procure the stuff that is needed to build the thruster. And hopefully, the thruster will be built by June next year, tested, and then we're gonna reach another TRL level for the tech. However, and this is important to mention, you need to look at this question of maturity from the global perspective. And the Kiwis are going to bring their thruster, one of the most important components of subsystems of the thruster is going to be tested at the International Space Station in February 2025. It's not going to be a whole system, what they're going to test, but they're going to test the superconducting coil with the flux pump, and experiments are going to be carried at the ISS, and then they're going to get it back, and they're going to integrate it to their current thruster. And then they could claim TRL 7 or 6, you see. And that means, in other words, they might be the first to market, even though neutral star systems started at first on this one, etc. But well, that's life.
True. So looking further down the road, where do you see NutriStar systems in the next 5 to 10 years?
Definitely not in Germany. And we need to look, and that's one of the main challenges we have at the moment. We need to look for a home base in Europe, where we can get a country and a government that is really support us, right? And that understand what we're doing, etc. That have been extremely difficult. The other option we have is we're trying to pivot at the moment to the United States and establish ourselves in the United States. We have a team there, and we won contracts with the Air Force Research Lab. So, and also a great deal of our traction is also coming from the United States. So, if we make it, I think we're going to make it in the United States for sure, or some other country. I don't. I have. It's. I mean, I'm an optimist by heart and by birth, but it's Germany is a quite complex environment to operate at the moment.
Wow. I didn't expect that answer, but yeah, I'm sure.
I mean, you can, yeah, you have to, you need to. I mean, this is something that you need to understand, and I think that this is something that investors sees today. You see, they see how difficult it is to articulate programs that drive demand, that create a commercial market. This is something that is not existing in Germany. You have initiative, yeah. You have in Munich. You have a lot of people. You have Rafaela Kraus pushing with base and defense, and you have Tum Venture Labs, pushing also there. But the reality is, um, the problem is at a political level. You see, it's a political decision. And every book about innovation will tell you the same. Innovation is a top-down approach. You see, it comes from from the top down to the people, and it's not bottom up. It never happens bottom up. Most of the entrepreneurs that do this, they don't have the means to push programs for increasing maturity level on space technologies. This is really expensive.
Mhm. Well, Manuel, this has been a fascinating conversation. As we come to the end, is there anything you'd like to share with our audience? Any exciting announcements or news from Neutron Star Systems?
I mean, I think that I don't know who your audience is going to be for, but for space entrepreneurs, I think my message is believe in yourself, and fucking believe in yourself.
So, and if people want to follow your work or your startup's work or keep up to date with the Neutron Star Systems, what's the best place for them to find you?
I mean, LinkedIn, we have our website, we have our YouTube channel, where we have some videos about our tech, about our vision. And I think that people wants to find me or find any one of us, they will do so.
Perfect. I'll put some in the description below.
Yeah, info at neutronstar.systems.
Perfect. Well, thank you so much for joining us today, Manuel.
Omar, thank you for having me
It's
and
been a
wish you all the
pleasure.
best.
Yeah, and to our listeners, thank you for tuning in. And until next time, this is Omar Alayli, and you've been listening to the Omar Alayli podcast. Keep exploring.